Saxon Advanced Mathematics, lesson 56. Listen, after you do this lesson, if you want to call CPS and report me for child abuse, you know, I'm not going to argue with you because this is a rigorous lesson and it's too long, and I call John out for putting too many topics into one. There's 3 different topics. It's kind of a workout. So feel free to pause me between, like I said, there's 3 different sections. If you want to pause after the first or the second and collect yourself, I don't blame you. I'll try to remember to tell you when we're switching gears, because you know me, I'll just plow straight ahead. They're not terribly difficult, but they're just, it's a lot. All right, let's talk about triangular areas. You know how to find the area of a triangle. The area of a triangle equals base times height divided by 2, right? You've known that for a long time. And you know that depending on the type of triangle, the height may be measured in a different way. These are the 3 different kinds of triangles that we have to deal with. And for each one of them, the height's in a different place. In order to find them, though, you use the good old spider trick. Send the spider up to the top of the triangle. And I mean that in a very unscientific way, right? Whatever the high point of the triangle is, send the spider up as high as he can go. Have the spider drop a web, the first line in its web, straight down. This one's right alongside of. That is where your height is, right? The spider is here to help us. This one is the weirdest because it actually goes outside of the triangle. Notice that the height always makes a right angle with the base of the triangle, okay? Now, when we were younger, back in the days of our innocence, our mathematical innocence, John had to give us the height. If he wanted us to find the area of a triangle, he better give us the height because we can't do it without it, right? Well, those days are officially over, and we're now expected to find our own heights. Find the area of this triangle. Ready? Here it comes, and you'll agree with me. There's no height. We've got the base, we've got this side, but we don't have a height. So what we have to do is make the height. We're gonna send in our spider. I have 6-legged spiders. I don't know how you feel about that. It's kind of weird, but it works for me. Somehow drawing an extra one just seems too messy. And we're gonna have that spider drop us down a line and create a right triangle right there. Now, the way I originally drew this wasn't a right triangle, was it? I just had my spider make it into one. Now, we need to know the length of this height, then we can multiply it by the base and we'll be fine, right? Well, here's the thing. Trig tools will help us do this, right? We're ignoring this other half of the triangle. We're only paying attention to this little right triangle that we made that looks like this. And we can see that if we want this opposite side, we can say the sine, oh, this is degrees, I should put that there. The sine of 42 degrees will equal h, or you could call it O, right, the opposite side, over our hypotenuse, which is 12. Oh, that changes things, doesn't it? And then we can say 12 times the sine of 42 degrees equals h. And we can grab our calculators and we can kick it through and we'll get h equals 8.03. Oh, lovely. Now we're ready to do this. Right? We know the base is 12. We've had that, or the base is 16 rather, sorry. There's the base C, right? We've had this all along. Now we've got the height, it's 8.03, so we can say 16 times 8.03 divided by 2 is the area of our triangle. I'm gonna write that. And if we simplify that, what I'm going to do is I'm going to reduce those and do 8. And I can see it's going to be the area equals, it's going to be 64.24, right? 64.24. I look for a unit. It's inches. It's squared. There's our answer. Okay? So the moral of the story is now that we have trig tools, we can find our own heights. We did it this time in this style of triangle, but it would work just as well in those. We just have to make a right triangle. And in fact, we're going to do it in a weird triangle now. Ready? The next problem is a weirdo triangle. All right, I'm going to do what I did last time, where I'm going to draw the problem that John gives us in green. Ready? It is a funky looking triangle. It's got a very small base. And then it goes way off on a tangent. Well, not a literal tangent, but you know what I mean. This is 14. This is 6. And this is 150 degrees. Okay. Well, we know that the area of a triangle equals base times height divided by 2. Might as well get the easy stuff written down. And we can see that our base is 6. We need our height. Let's draw it in. Here's our spider. I mean, if you don't draw the spider every time, I'm going to be sad, because the spider really adds to this whole scenario we got going here. There he is. And I extend it here. And I go, oh yeah, you're a right triangle. Now, this one's different because in order to use our trig functions, we need the right triangle. So now we're paying attention to this triangle and we're ignoring that part. That doesn't help us. That's not the right triangle. This is the right triangle. Notice there's our hypotenuse. And here's where we can find our angle. Blue is all the stuff we had to figure out. If this is 150 and this is a straight line, this has to be a 30-degree angle. And this 14 relates to that side. That's our hypotenuse, right? So we can write, and I'm going to write this, I'm going to cut to the chase in this one. I'm going to write, no, I'm not. It's just too confusing. Sine of 30 degrees equals the opposite side, that's the height, over 14, that's the hypotenuse. I'll put an H here to remind you that this side is the height that we're looking for. All right. Now I can cross multiply and bring that up. 14 times the sine of 30 degrees equals H. We grab a calculator, we enter 30, we hit sine times 14, and we get that the sine, this number, H, equals 7. Boy, it's not often that a trig function comes out so clean and simple, does it? But that's a happy thing. So now we can take that over area equals base times height. We already said our base was 6. Our height is 7. We're going to divide by 2. So our answer equals, I cancel here and I get a 3, 21 meters squared is our final answer. Yay. It's kind of fun, isn't it? In a weird little way. I mean, I think it's all fun. I'm sorry. I do. One of my Algebra 2 students this week asked me for help. He had a list of about 10 or 12 problems that he had gotten stuck on. They were problems from before Christmas, and he had not followed up on getting answers to them, so he gave them to me all in a clump and was very apologetic, thinking that I would not appreciate him giving me all these old problems to solve. What he didn't know is that I love doing problems. And so I had so much fun sitting here working through all those problems. And then I took pictures of my work. That's me taking pictures. I took pictures of my work and sent them to him and just was totally entertained for an hour or so that night. So if you ever want to ask me questions, just know I love answering them. Find the area of this trapezoid. Trapezoid, what? Who said we were doing trapezoids? Well, fine, let's look at it. We were talking about triangles, not trapezoids, right? Okay, here it is. This is asymmetrical. It's just a wonky thing. This is in meters. 5, 4, 29 degrees. That's helpful. 10. Okay, we know that's the base. Now, how do we figure out trapezoids? What are we going to do with that? All right. Remember that the secret to doing these is to divide them into two triangles. There's two ways we could do that. We could divide it this way, or we could divide it this way. Now, if we knew the height, either way would be fine. But I know we're going to need this angle to use a trig function to calculate a height. So I don't want to run my diagonal through this way because then that's going to divide that up and that's going to make a big mess. So I would rather divide my triangle this way. And then I'm going to find the height, right? This will be my triangle. Here's my spider up top. I'm going to drop his line down and I'm going to use the 29 degrees to find this. This will be the height, right? And then when I go to do this other triangle, and I'll drop a spider from him as well, and it'll be like that. This will be the same height. So I don't have to do two calculations. I can just calculate the height once and use it for triangle A and then again for triangle B. All right, that might make more sense as we go. So I need to find the height just like we have in the past ones. So here we are. We know that it's going to be the opposite again. So this time I'm just going to put my hypotenuse right in front of my function. The 5 times the sine of 29 degrees will give me the height, right? Instead of putting this underneath, I'm popping it right up there. Let's make life easier for ourselves. Oh, I should have been doing that before. I was thinking you guys were the Algebra 2 class and they are just learning trig functions, but you're seasoned pros. You don't need to write that as a fraction. You can pop the hypotenuse right up here and be calculator ready in one go. This gives us then a height of 2.92. We're in meters, but we don't need that yet. Okay, so for triangle A, we're going to do the base of 10 times the height of 2.92. And we'll divide that by 2. Oh, I'm sorry, it's 2.42. Yeah. Sorry, that 9 got me off on the wrong track. Sorry about that. Okay, so it's 2.42. And so if we multiply here, what I'm doing is I am mentally dividing the 2 into this. I get 1.21, and then I move the decimal place over, and this gives me 12.1. See how I did that? I divided into this mentally, which was super easy, 121, then bumped the decimal over, 121. Okay, so that's the area of triangle A. Triangle B, let's see, the base of this one is this side, so it's 4, right? The height is the same, 2.42. Don't try and trick me again. Divide it by 2. This one, I'm going to do this. I'm going to cancel these two against each other and get a 2, and then I'll double that. So this will become 4.84. And then I'm going to put a 0 in here so that when I add, everything will line up nicely. 4, 9, 16. Our unit is meters. We're finding an area, so it's squared, and that is my answer. Is it right? Yay, it is. Beautiful. Make sense? So even though this is a trapezoid, we divide it into two triangles. We divide wisely because, like I said, the other option would have been to divide like this. This is our angle that we need. We don't want to mess that up. That would have ruined things for us. So that's why I chose to divide this way. And then the height we could use for both. All right, guess what? We're ready to switch gears to the second topic. Hopefully that did not blow your mind too much. Because now we're going to talk about areas of segments. Actually, if you can hang on through this one, the third one is the more disconnected. So that would be the better time to take the break. I mean, take two if you want. I'm going to start on our second topic, which is area of segments. Pause me if you like. All right. First of all, we have to ask ourselves, what is a segment? Let me draw a picture. Here's a circle. So far, so good, right? Here is the center. Here is what we called a central angle fairly recently, although maybe that was the other class, sorry. These two are both radii, plural of radius. They're both radiuses, which isn't really a word. If we connect the endpoints of the radii, we create a lovely little triangle, right? And if we wanted, we could find the height of this. This area here, that's outside the triangle, this curved bit, that is called the segment. Okay? Not to be confused with this whole thing, which we call a sector, and I always think of it as the pizza slice. Okay? So the triangle plus the segment is the sector. The segment alone is the segment, right? It's the little curvy crescent bit on the edge. All right? Remember that if we want to find the size of the sector, we take the central angle and we make a fraction of that with 360. Like, let's just pretend this is 70 degrees. We would write 70 over 360, and then we would multiply that by pi r squared. This part tells us the size of the sector, right? Because it's a proportion of what we want over the whole circle. This part tells us the area of the circle. So here's the area of the whole circle, and then we multiply it by a fraction that represents the part we're interested in, right? Now, this makes sense when we're measuring our circle and our angles in degrees, right? But our central angle can also be measured in radians. Are you groaning right now? It's not that bad though. If we're measuring our angles in radians instead of degrees, then all we do is we take the measure of our central angle and we divide it by 2 pi instead of 360. So it's not that different, right? During this class, I understand that most students really, I wouldn't say struggle with radians, but just kind of hate radians. They feel like intruders and aliens, and we'd much rather do degrees. I have been reviewing with one of my students who took this class last year and is preparing for college work, and we've been doing problems that last year she always did in degrees, and because she hated radians, and this year she's like, oh, let's do radians. I like radians, they're fine. So this too will happen to you. Okay, so what we're gonna do in finding the area of segments is we're gonna find the area of the sector, the whole pizza slice, using this formula, and then we're gonna find the area of the triangle and subtract it out. Whoa, right? Let me write that up here. So it'll sort of be in front of you. We'll find the area of the sector, that's the pizza slice, and then we'll subtract the area of the triangle. And we just learned how to find our own heights so that when we're finding the area of a triangle, if we don't have it, we can get it. And then that, when we subtract it, that will give us what we call the segment, that little crescent edge along, right? And I'll just draw a little picture. Okay. Oh, that is not the middle. Ignore that. Okay, so we'll find the area of the sector, and then we'll subtract out the area of the triangle, and that will give us the area of the segment. I didn't write that. Okay, that's what we're doing. That doesn't exist. It's just a little freckle. Okay, ready? Let's try it. Example 56.4. Let me just check on something for you. There's only this one example, so if you haven't taken a break yet and you're feeling like you're getting ready to fall down, here we go. All right. Find the area of the segment shown above. So I've got a picture for you. No, it's the same. If the central angle is 0.6 radians, and the radius is 10 feet. Okay, let's write that down. The picture he drew is just like the ones I've been drawing, so NBD. Central angle equals 0.6 radians. Okay, so we're not doing degrees, we're doing radians. Buckle in, and the radius equals 10 feet, okay? At least that's a nice, easy number. So let me draw another picture. I'm going to draw it fairly big so we can see what we're doing. And this time, I'm going to change the way I draw the picture. That will make it a little more helpful for you. See how here I drew the bottom part of our triangle tipped? This time I'm going to make that radius go perfectly straight across. It doesn't matter in terms of the math, but it will help you visualize much better. So I'm always going to make this rectangle the base of the triangle is going to be a straight line. And then I'm going up like that, okay? So we know that the radii are 10. That's going to be helpful to me. We know that we're going to draw a triangle by closing off the segment. We know that this angle equals 0.6 radians, right? And we're trying to find the area of the segment. So we're trying to find this. So we'll be using this. The first thing we need to do is find the area of the sector. And we discussed on the last page that what we do, here, let's do this. The area of the sector is we take the measure of our central angle, which is 0.6, and we put it over the whole circle, which is 2 pi. And then we multiply it by pi r squared, the area of the whole circle. So it will be times pi r squared. R is 10, so that's 100. That looks like a weird order, but I'm just leaving it like that. Now, look what happens. This is the area of the sector, right? We're finding this whole pizza slice. That's our angle. That's the whole circle. This is the area of the whole circle. When I multiply this through, that will give me the whole pizza slice. I know I'm repeating myself, but I also know this is super confusing. Okay, so look, let's cancel those. Let's cancel the 2 against the 6 and make that a 0.3. And then let's use this 100 to bump this decimal place 2 times. So we'll need a 0 to fill in. So the area of the sector is 30, what's our unit? Feet. Feet squared. Okay, that's important. We've got the first component done. Yay. Now I'm going to switch colors so that we can see the second step as separately. So that was my first thing. I found the area of the sector. Now I'm going to find the area of the triangle. I'll do that over here. Spider, where are you? Climb up. There he is. He drops, he or she, drop that first one straight down. It's not as perfect as it should be because it doesn't go right down the middle, but it's okay. This is an angle and, okay, so to find this angle, we know that that's 0.6 radians. We know we want, this is the opposite, so, and that's the hypotenuse, so 10 times the sine of 0.6 radians. Now, I don't know if you've discovered this, but on your calculator, there is a way to toggle back and forth between radians and degrees. It's in the upper left corner of your keyboard. I think, oh, I wish I had it in front of me. If you're stuck at all, Google how to change from radians, from degrees to radians on a calculator. You want to set your trig functions for rads, and then it works exactly the same. 0.6 sine times 10, okay? Let me know if you have any trouble with that, and I will help you. But the calculation works exactly the same. You just have to change the setting, and what you will get is that the hypotenuse, this whole thing will be equal to the hypotenuse, and when you run that number through, the hypotenuse should be 5.65. I'm sorry, not hypotenuse, height. The hypotenuse is 10, we already knew that, right? So 5.65 is the height of our triangle. So then when we go base times height, we know the base is 10. So the area of the whole triangle will be the base, 10, times the height, 5.65, divided by 2. We see we can cancel those, but let's not even fool around with trying to do all of this by hand. We're in too deep to get sidetracked with hand calculations. That will be 28.25, again, feet squared. It's the area of the triangle, okay? And I'm just gonna go back. I wanna label this again. This is the area of the sector. I'm gonna write that as like a little subscript. This is the area of the triangle. We are just about there, aren't we? Because now, all we need to do is subtract. Where do I have room to do that? I'm gonna do it up here. I'm gonna do it in a third color so that you'll be incredibly confused. No, you won't. You've got this. The third step is to subtract. So we take the area of the sector, which is right here, 30, and I'm gonna put some decimal places in there. And we're gonna subtract the area of the triangle, remembering, right, We have the whole thing, the whole pizza, and we're cutting out the triangle, and that will give us that little bit. Same thing here, right? The area of the triangle is 28.25, and we are subtracting that. And so the area of the sector is 1.75 feet squared area of the, I'm sorry, I think I said sector, I meant segment. This is the little skinny bit on the outside edge. This is the crust of the pizza that you don't want to eat. And guess what? That's right. Whew. That's a lot of steps, isn't it? Remember, this is the basic calculation that we're working toward. Let me, puffy cloud of knowledge, that. The area of the sector, the formula is right here. The area of the triangle, you know, is base times height divided by 2, and we practiced measuring the height on that. That's why we had to do that other section first. And then you simply subtract to get the area of the segment, all right? That's a workout. Take a break and come back to join me for section 3C, technically, which has nothing to do with this calculation. Okay. Our last section is called Systems of Inequalities. And this is one, I think it'll be easier for me to show you in the book. All right. We did these last year, near the end. And remember, what's happening here is that John has graphed for us two shapes. In this one, which is our first example, he's given us a line right through there, and he's graphed this parabola for us. We don't have to do the heavy lifting. Thanks, John. But they're inequalities. They're not equal signs. And so what we're trying to do is assess what area of the line would be included in this equality, what area of the graph would be included in the parabola, and where do they overlap, right? So let me remind you of a couple general rules of thumb. When we say that y is greater than, we tend to go up the y-axis because we want the y's going greater. When we say y is greater than a parabola, we generally mean the outside because, again, that's where we can go up the parabola. Of course, that's a downward facing parabola. So what you're looking for is if y is greater than, then you look at the region where y is allowed to go up, right? So in this case, y is greater than the line, so that would mean above. And y is greater than the parabola, so that would mean outside the parabola. So that looks like area A, doesn't it? Is the area where those two things overlap. And that is correct. However, what we like to do before we just rashly look at the answer based on our guesses is we choose one point to test. All right? Now, I like to test with the origin because it's really easy to plug zeros into equations, right? It's so easy. So whenever possible, I like to use the origin, and I look at my picture first. In this case, if it's region A, as I suspect, then the origin should work out. It should be true for both of these, right? So let's try it. This is the part where students always get annoyed because it's more tedious. But the other part, you just get to look at the book. So it's okay if we do a little heavy lifting. 56.5. So the first equation is y is greater than or equal to, sorry, I don't like when I chat out loud. That's unnecessary. So I'm testing with 0, 0, right? Again, we can choose any point we want for our test point. It's just that the zeros are so delightful. So when we plug that in, 0 is greater than or equal to 1/2 times 0 minus 4. That all goes away. Is 0 greater than minus 4? Yeah, it is. So in this one, it's true. For the first equation in this picture. Now we have to test the second one, the parabola. Y is greater than or equal to, oh, I'm doing it again, aren't I? We'll plug in the zeros again. That's a squared. Okay, this is just a 0. This is just a 0. 0 is greater than -1, also true. So that proves our theory. That proves our theory that the origin should be part of the solution, because when we tested the origin, which is in region 1, it was true for both of these. So that's our indication that our theory is correct. So we say it's region A, we flip, and we see, oh look, it's region A. Now, we got the right answer. If you look at this though, this is John's test. Notice that his both came true. He used a different point. He used 0, 5. Well, you know what I say? Bully for John. That's cool. You can use any test point you want. There's no law about what test point you use. Typically what we do is we choose a test point in the region that we think is the right answer, and then we hope that it comes true. Let's do another one. This one's messier, isn't it? Okay, again, and this is the nice part of these problems. John does all the graphing work for us. We don't have to do that. We've got a parabola. This one opens up. Okay. We want y is greater than that. Okay, so y is greater than that tells me to choose the the y is going greater, and that's the inside of the parabola. So I think I want to choose between A and C. Notice that B and D are out here. Okay, so I want the inside of the parabola, then y is less than for the line. Well, less than with the y's usually means it's below. So I want inside the parabola but below the line. I think I want region C, all right? Now, I don't want to use the test point or the origin for this because it's not going to be true, right? The origin doesn't lie inside my zone. So I'll use what John chose. He used -2 and 1. Those aren't my favorite numbers, but let's just try them. So we're going to use that as our test point this time because it lies in the region that we think is correct. I can't use the origin because the origin isn't in region C. And that just makes me sad. But so be it, Jedi. All right. So this we said was region A. So here is example, 56.6. And our test point is going to be, what did I say, -2, 1, right? Again, that's just random. I took it because it was right there staring in front of us. So now we copy down the inequalities. Y, and I'm just going to plug these right in. I wrote them first and then I plugged them in. I'll do that again. I like to show you how to make it shorter, but if I show too many shortcuts right away, then it's likely that your brain could explode, and I don't want that. All right, so I want to plug in -2 for the x's, and it goes inside a quantity box, right? Okay, so then this becomes 4 minus 8 plus 2, and that equals 10 . 4 minus 8 is -4. Oh, what am I saying? Look, that's a 6, but it's supposed to be a 2. Huh, that makes a difference, doesn't it? No wonder, I'm like, this test is failing. 4 minus 8 is -4 plus 2 is still -2. 1 is greater than -2. This one is true. All right, so far so good. Our other equation that we have to test, or it's not an equation, it's an inequality. My bad. Y is less than -x plus 1. Again, we use these as our x and y. So we say 1 is less than minus 2 plus 1. Well, minus 2 is 2 plus 1, so that's 1 is less than 3, right? Also true. So that tells us that our guess was correct. Let me show you the picture again. Our guess was correct. Our test point verifies our hypothesis. Region C is the right answer. Ooh, John. He agrees. So that is C. Most students find these problems somewhat enjoyable because there isn't a lot of calculation. We mostly just look at the picture. Oh, there's one more. Oh my gosh. Have you died yet? I have to say, I enjoy these lessons. They could go on forever and I'd be delighted, but I know that your brain is seeing all this for the first time. Mine's seeing it for like what, the 18th time? So it's fun. Okay, here's one more. What region contains the coordinates of the point that satisfy the given system of equations? Blah, 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 blah. Okay, we have a circle and a line. Okay, now this circle equation looks a little different. We know that there's an x squared and a y squared. This we know is the radius squared. If it's less than, that generally means the inside of the circle. All right, the inside of the circle, because the radius is greater than these, right? That's your hint. The line, it's the same. If y is greater than, then we want to go up the y-axis. Whoop. So inside the circle, but above the line is my guess. Now, the origin lies right on the line. That's too tricky. We don't want to use that. It's just too close. John chooses -2, +2. He chooses that point. I don't want to use 2's. Let's use -1, +1. I think that is a better point. And we think it's region B, right? Because it's inside the circle, because the radius is greater than. This number, remember, is the radius squared. So it tells us we're inside the circle. And then this tells us we're above the line. That's B. Our point is -1, 1. Let's go. Okay, first inequality, x squared plus y squared is less than or equal to 16. Oh, well, this is going to work out pretty well, right? -1 squared plus 1 squared is less than 16. I feel pretty safe saying that's true. 1 plus 1 is less than 16, less than or equal to. True. All right, let's try the line. Y is greater than or equal to x. This is the x, this is the y. We have to be careful when we plug these in, don't we? 1 is greater than or equal to -1. Oh, well, totally true. That proves that this point does lie within the proper region. And so we look back at the picture and go, oh yeah, that was in B, so we think B is the right answer. Dun, 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 dun. B. Yay. Guess what? You survived. You're done. These are all correct. I haven't been smiley facing, have I? That I smiley faced. These are both correct as well. Got to get as much satisfaction as possible out of this process. Okay, guess what? You survived 56. You survived the end of week 15, the second week since the new year. Yay. If you are hanging on to this information, if you feel like you're fighting to stay in control of this, but yeah, you kind of get it, you're doing a fantastic job. This is a lot of material. This is we're pretty much into college level material at this point. A lot of this information is not considered high school mathematics. You have really stepped up. And if you're a high school student, studying college level math, I salute you. It's fantastic. So pat yourself on the back. Go do something nice for yourself. Listening to music would be ideal right now. Or if you like to draw or paint in any capacity, you know, draw some anime, do some doodles, fantastic. Go do something creative. It will restore the balance in your mind. We just were super left-brained, so go be right-brained for a while and exercise some creativity before you try to use your brain for anything else. Yay, we're done. Thank you, goodbye.